have two visitors from Japan, from Kyoto University. So Professor Yosuke Namikata, sorry, Yosuke Yamashiki. The Namikata, that's another collaborator. So yeah,
he's in Japan.
Yeah, he's in Japan. Yeah, but we'll meet here. Yeah, in September. So yeah, Professor Yamashiki is the director of the Graduate School on Human Habitability. So assessing the global risks. One of the risks, of course, is our sun, ionizing radiation. And so they have a pretty large variety of topics. So doing the field studies, theoretical studies, and even building the biosphere too. They're trying to understand how people can survive on Mars and doing projects on lunar settlement. So the whole range of the projects. And so Professor Yamashiki received his PhD in 1999, and so since that time he was at Kyoto University, and now he's directing this project. So he is involved in a number of projects. It's hydraulic projects, and some of the projects related to our Earth, some of the projects related to the assessment of ionizing radiation of Fukushima, after the Fukushima, a problem that they had, the incidents. And but then he moved his attention to astrophysics and habitability. So that's one of the projects that we're doing together. And another person I want to introduce is a young scientist. He just graduated in master degree program and began assessing this ionizing radiation on the environments of the moon. And now she's just a recent PhD student that's going to work with us on our projects. Yeah, please.
Thank you very much. Thank you. I came here in 2019. It was my second or third visit actually, and I appreciate that I have got the opportunity to talk in front of you. I'm not the director of the insights, but I'm a department head of the.
Oh,
but thank you.
Sorry.
However, yeah, I'm organizing a center, the center of the study of this. Yeah, center. Okay. So that center, the Human Spacetology Center, focusing on several projects, including the manned mission to the space. We hire there is a former astronaut who is focusing on now about the development of the building satellite, which will be launched very soon. Today, I'm going to give a talk about the impact of ionizing radiation of habitability induced by solar and stellar energetic particles. And that study actually has been accomplished in 2019. We have now extended phase, which has not been yet published because I have to fix some of the problem, but now I'm fixing, and I'd like to introduce this in front of you the first time. So I have my talk will be focusing on first of all about impact of the habitability into the exoplanet, and that is the first thing. And the second thing is impact of the ionizing radiation in the past, the ancient Earth. And the third thing is the impact on the aviation, right? So three different things I will talk in front of you. Yeah, the first of all, the reason why we are focusing on this topic is ENDO. Relatively, it's a small stars, but it's very active, magnetically very active because of the very developed convective layer, and they have a very frequent superflare and very, very small. And also the habitability of those kind of stars are relatively very close to the stars. And most of the habitable planet found recently is around the ENDO because of the transit, very short period of the transit. It is easy to access. However, if you think about the habitability, you have to think about how much energy, energetic particle will be released from this kind of stuff and what is the impact. So we have developed a kind of a systematic analysis tools including the software that we have developed.
Can you, the mic,
Yeah,
the volume is like.
yeah.
lower part
If
of
you
the
have a microphone or
No, it should all be coming from here.
yeah.
Okay. Sorry, I'm sorry.
Yeah, sorry.
Yeah,
It's okay.
Hey Dylan, for us online, we can't hear anything.
My colleague, and we have used those relationships in order to approximate the frequency and also the magnitude. But however, when you think about the relationship between the star and planet, we have to make a kind of a simplification because it is almost very difficult things. You can make a MHD for all the star system. Of course, there are some of the star you can do. I think the Vladimir has already accomplished some of the MHD simulation for some of the star. But if you have many, I think it is good idea to make a very simple approximation. How those CME can inject from the center of the star. So we hypothesize that the proton can be released from the center of the star in a certain angle, like 15 degree, and then in the horizontal area with the same of the planetary disk, so that using this approximation and also the area, the horizontal area for the stellar ejector might be like 90 to 108 degree from the center of the star. Then we can approximate the frequency of that happening. And also we can approximate the spectra of the center of the star. And that the initial part, I will introduce a past study that we have used the two different spectra. One is the GLE43, in which occurred 1989, and other is a Carrington event. So those two solar GLE ground level enchantment event are being studied very in detail and making the spectrum like this two curve. By using this two curve and amplifying, this is the relationship between the star spot area and also the frequency, real energy and frequency. So by using this relationship that have been found by Hara and also the user node, you can approximate depending upon the activity of the different star system by using the simple parameter of the star spot area. So by using this relationship, and then we have determined the annual maximum flare, which may occur during 1 year of the Earth, the terrestrial year, not the planetary year, because the planetary year might be very short, like 10 days or 15 days. So in order to unify all the dimensions, you have to use the terrestrial value. So we use the annual maximum flare value. And also the spot maximum value flare might be determined according to the stellar star spot, how much energy in theoretically that kind of star can release within a certain year. Certain year might be 100 or 10,000, many years. Right? And also there is a possible maximum field. Might be this is showing the total capacity of the star, which can emit a very, very strong field. However, in the practical sense, this you don't have to discuss about this. I think that the previous two value, annual maximum field and spot maximum field, might be the one that we are looking at. And then we use the code, which is the FITS. It's developed by Sato, and this is a multi-cloud simulation code. So we use the spectrum as the boundary condition of the planetary boundary, and then we calculated estimated load in the different atmospheric type and different magnetic condition. However, we only simplify the magnetic condition, like we approximate, we make a kind of a simple hypothesis that that kind of planet may have a dipole magnetosphere like Earth, and then we just use other filter, right? Because most of the energetic particle is positively charged, like proton, so the proton can be like bented according to the magnetosphere, like the Earth, and most of the dangerous particle may be going to the polar region, like the Earth. This is a simple approximation because we don't have any information about the magnetic condition of the exoplanet. So this is the quick picture of the Iophedium, but there are secondary air shower generated by the particles. Right? And field codes have been developed by Tatsuhiko Sato, and see the particle and heavy ion transport code system. It's a kind of a Monte-Carlo simulation code, but this is a very, very detailed code. So we cannot solve this fits for entire solar system, but we only can solve the fits code into the individual planet. In this case, we only solve like Earth-like planet, and then we change the magnetic condition and also the atmospheric condition. So the first study that we have done is a stellar superflare. We have estimated it's an ICME and also the stellar proton event, and then they will penetrate into the typical planetary atmosphere. So atmosphere, we have made three typical type of the atmosphere. It's a hydrogen atmosphere and carbon dioxide atmosphere, and also the terrestrial type atmosphere, which is composed by the nitrogen and oxygen, 80% nitrogen and 20% of the oxygen. Of course, this might be only few cases on the planet, but we have to like standardize that terrestrial type atmosphere might be the one which is typical of the universe. We don't know sure, but we have to do that. But fortunately, it's a kind of a good condition is the carbon dioxide dominant atmosphere and also the terrestrial type atmosphere has similar tendency in the absorption of those kind of particles, right? And in the initial study, we only use the two types of the spectrum, like the harder spectrum here 43 and softer spectrum in Carrington event. And we, at that period, we selected these planets, like Kepler 283, 1638, and Proxima Centauri, and TRAPPIST systems, right? And then the initial study, actually the Barton star, this is already kick out from the list of the confirmed planet. But at that period, we did a study. So at that period, what we have done is like we made a comparison with a different planetary system and calculated the total dose depending on the different atmospheric depths by using the DLE 43, and also this is the Carrington event, and this is the annual maximum flare event, and this is the spot maximum flare event, which means this is a little bit smaller and this is the harder. Right. So taking a look at the individual result, this one is showing like I think it's I cannot prove this. I'm sorry, but you can say this is in the x-axis showing the atmospheric depth. So if you here is a 1 bar, it's with 1,000 gram per centimeter of the atmosphere. And this red line represents the Martian surface atmosphere. And this is 1/10 of the terrestrial pressure, which we determine as a possible exoplanetary surface, which means the sum of the exoplanet may have lost the atmosphere because of the atmospheric escape effect. So, for example, Proxima Centauri, if you put the whole complete atmosphere at the Earth, the dose become very, very small. It's only 0.43 millisievert, which is almost negligible because it is very, very normal in the situation like Earth. And TRAPPIST-1P is also the same. So generally, if the atmosphere pressure is high, you don't have to worry about even though those habitable planets are orbiting the envelope. This was the first important emission result. However, so if you think about the impact of the atmospheric escape, so the atmospheric escape might be in proportion to the strength of the XUV. If the XUV is very strong, that means that probably most of the atmosphere may have lost because of the atmospheric escape impact. So if you, for example, talking about the Proxima Centauri, if they have XUV flux, which is 76 times higher compared to that of the stars. So, which means if you are in the Proxima Centauri, if the production of the atmosphere is not sufficient, the most of the atmosphere might have been gone. So, if you in that condition, if you think about the atmospheric pressure of the Proxima Centauri is just 1/10, that critical dose, annual dose become 8.9 sievert. So fatal dose for the human is considered from 7 to 10 sievert. So if you receive 7 sievert radiation, the whole human cannot survive because after several days because of the impact. But if you think it's a 10 sievert, might be the fatal dose, it is universal type. Of course, if you think about the different type of the organs, it is not the 10 sievert, like a different type of the organ can survive like a 1,000 sievert or 1,000 gray. But in this case, we have just So about the TRAPPIST is the same. It's a very high atmospheric escape ratio. It's a 65 times higher. So this was the conclusion when we have 2019, the last presentation I gave a talk about that. However, and I get the important information from Rapedian. Doctor, who is here? Oh, okay. So thank you for Dr. Hu. So we use his calculation result. Like there are some very important calculation carried out by Dr. Hu and Vladimir, and they made a kind of a hypothetical superflare which may happen in the Earth-like, sun-like stars. By the different condition, they set up like the maximum velocity of the flare ejection, and also the density of the proton for each condition. So there are 12 cases, typical cases, starting from M1 to M3. So M1 in this this is more harder condition with the velocity, and also. And then we set up the different type of the calculation, which mean, for example, this is the Kepler 283, which orbiting Kyoto. So, and this is the only Kepler habitable planet found in the Kepler system. Of course, there is a Kepler 452 and a different Kepler 62, but the Kepler 283 is one of the planets which can be habitable. And also we have detected some of the stellar flare from this center of the star. In that case, so in the previous study, if you use the GLE 43, the maximum dose is just 83 millisievert. This is not even in the 1/10 of the pressure, which means the Kepler 283 using the terrestrial or solar system of the spectra, it is not dangerous at all. So, however, if you apply like N to B scenario of the super flare, and then the dose become raised to the 94 sievert, and this is very, very strong, and it is fatal. Even if you in that condition with the terrestrial atmospheric pressure, the under Earth atmospheric pressure reach 19 millisievert, and 20 millisievert is like a limit for the occupation exposure, occupation levels dose. So which means in the Kepler 283c might be not habitable if you think about the super flare, which has much harder spectrum. And also there are other conditions. Proxima Centauri B, of course, this was calculated as a fatal in the past study. However, if you use the M1D, it's a different scenario. The critical value become higher. It's a 91 sievert. It is a very, very strong, and the loss 1 to 8. This is considered as a safe planet because it relatively it is a calm and a small flare. And then we will discuss about TRAPPIST-1 system. TRAPPIST-1 system is considered nowadays. They have discussion that TRAPPIST-1 system is not habitable at all because of the very few atmosphere found even by the I think it's James Webb Space Telescope. We don't know, but we have already taught that the atmospheric escape rate of the TRAPPIST system is very high because of the high X-UV fluxes. But if you utilize that spectrum calculated by food, the dose induced by the annual flare reached far fatal. It's a 272 sievert. It is very, very high. Of course, that could be if you have a same atmospheric pressure with Earth, still it's a 51 millisievert. So, which means if you just sitting on the planet, you will receive fatal dose from the center of the star. That is kind of terrible. The only condition. Yeah.
When are you saying like it is fatal for? Means I'm just asking what is the planetary magnetic field?
Okay. Yeah. actually, this simulation is just without considering the planetary magnetic field, right? So no planet magnetic protection, right?
Oh,
Yeah, I can show you later on if the magnetic filter may works because it can reduce the fatal dose. And also, if you have a higher, thicker atmospheric pressure, then the dose become lower. Yeah, sorry. And all my presentation right now is without considering the magnetic impact. If you have magnetosphere, it is the same as Earth. The dose become like less than 10% or 5%.
oh, wonderful.
It's reduced significantly. It's very important. So in this case, for example, just flying it's become 27 series or something. But if you have a same. But of course, individual values we don't know, but just making comparison. Right. So, for example, GJ163, it is very, sorry. They have like a very high atmospheric escape rate. But if you have calculated with this stellar flare, the dose become very hard. Okay, so this is the first study, and I will show you the complete panel of habitable planet later on. But I'd like to move to the second topic. The second topic is aviation exposure. So aviation exposure can be calculated by the two different ways. One is a very simplified terrestrial atmosphere, and calculated the dose for the entire, like 10 years, 10 hours of the flight. And the second thing is we can use a very complicated, complex, and sufficient 3D those reprocessed and also reconstructed magnetic field, and also the dose field, 3-dimensional, and also with the time it's a 4-dimensional spatial and 1 temporal dimension of the dose rate for the 5 different GLE events. And that is it is a completely different study with the previous one, because the previous study, we just think about very general, and because we don't have any planetary mapping. But if you think about the terrestrial map, you have to think about very detailed magnetic information and also the picture. So we use 5 different GLE 60, 69, 70, 71, 72. So on this, the GLE 69, which occurred in 2005, was the most typical and most harder spectrum. And what this picture means, so that all aviation event, you will receive the dose from the galactic cosmic ray, because we are exposed to the galactic cosmic ray. Galactic cosmic ray, of course, vary. When the sun is active, the GCR become lower, but when the sun was not active, the GCR become higher. It's an opposite. On the other hand, when the sun is active, there is a solar energetic particle event coming and attacking the flight. So the GCR can be like constant. So if you fly from like Tokyo to New York or Tokyo to Washington, so the dose is a constant. Like if you start from 6 p.m. or 8 p.m., it doesn't change because the GCR is almost constant. However, think about that. If you have one big superflare occurs at a certain period, that particle coming from the sun may reach the Earth, but they will penetrate depending upon the magnetosphere and affected by the magnetosphere and also the time. So that is like those is time dependent and also the place dependent, of course, because they are affected by the Earth's magnetosphere. So we calculated together with the support team, so they developed complete four-dimensional temporal calculation. And then we project all the flight path. The flight path will be depending on the when they leave, then they depart. Likewise, if the flight departing at noon, so at the noon they are still in Tokyo, but when they lead to the polar region, like all the flight will pass the polar region, right? The polar region is very vulnerable for the electric particle. So depending upon when they pass the North Pole and South Pole, their dose become surge or constant. So actually, the aviation exposure will be depending upon the time and also the cause and also the typical peak. So we made 5 different GL events for the time, and we set up several scenarios for each bus and each 10 minutes of the time. And then we made a maximum dose for each event. So, and then like this way, this is GL60. So GL60 is not so hard event. So this is the GCL dose, the accumulate cumulative GCL dose. And it doesn't change. When you have a set event, of course the total dose become higher, but it doesn't become like too high because the GL 60 is a normal. But the GL 69 is a harder event. So they typically increase the dose. And this is a cumulative dose, and this is a instant dose. So the GL 69 have a higher. So we did, and also to make the extension of the probability, we extended GLE probability for the past and also the present, and using 775 Miyake event and also the 99915. So if you don't have this event, we cannot calculate actually the probability. But this line, why we create this line? Because the probability is not enough. Probability of the occurrence of the theory is not enough. What we need for the dose calculation, we have to have a probability and also the duration and also the maximum intensity of the neutron. So the GLE event, they recorded the higher neutron event. So if the neutron increase rate is higher, we consider that the GLE at the higher energy. So which means that we determine peak event intensity and also the event integrated intensity. Event integrated intensity is just I think that was determined with a different person, but this is the integration of the duration of the GLE and also the increased ratio of the neutron energy. So, but of course, we don't know the somebody talk? Oh, yeah. So of course, we don't have information about the Miyake event, but we appreciate the Miyake event might have 160 times higher event. So we just multiply it, and this is a hypothetical value we extracted from that other research. And then we calculated this, and using this probability, we have research study and also So our conclusion is that to minimize the flight dose, you can only decrease the height from because the normal flight fly 12 kilometers above the sea level. However, during the prayer time, if that flight can fly 9.5 kilometers above the sea level, the dose becomes significantly weak because of the secondary air shower impact. So the conclusion is not written here, I'm sorry, because this has been published by the scientific report in the Nature publication. So you can take a look at that. However, that publication has been made in 2022, and we didn't think about a very high and also the typical peak of induced by the superfluid, which has much harder event. So the conclusion might change if you apply for the more harder spectrum. So our conclusion was the one which we didn't use the hypothetical field. Only we use the observed field to reconstruct. So the conclusion might change if we apply for the different one. So the next one is for the past Earth, which is when you have like a young sun might have a very typical and hard and event that we have hypothesizing the activity of the young sun. But at that period, I use the star spot, hypothetical star spot, and also the annual maximum flare in the past sun. Like it might be the 10 power 34 elves, and we use the spectrum calculated by Dr. Hu, and we did those kinds of simulation from the young sun to the current sun. So, for example, here, if you use like the normal spectrum observed by the Earth, the past Earth is not harsh condition at all, because like if you are thinking Earth from 100 million years, it is still not fatal and very not dangerous at all. But if you utilize like GLE5 and also the synthetic flare, synthetic spectrum like N3C, that the past Earth become harsh condition for the in terms of the dose. Likewise, if you utilize like N3C, and if you hypothesizing very low atmospheric pressure, then for example here, that dose level reaches almost fatal level. However, this dose is very high. However, this is not fatal for all living creatures yet, because at that period, of course, there is no human and no complex animals. There are only I think the eukaryotes, right? Prokaryote, right? So the prokaryotes, right? Prokaryotes is very resistant against radiation. So if you discuss about this, we have to think about the different hypotheses. So that calculation now we are doing, because the dose, those kind of dose, of course, it's hard. It's difficult for the complex animal, but it might be the key to create the living creature in the different way. So we have to nowadays. Now we are trying to approximate how those kind of radiation might be the key for the life, whether the life can start or life can be dead. And it is a little bit complicated calculation that we are trying to do. And also using the primordial atmospheric condition, right? So that in this calculation, our condition is like it is not completely fatal. However, this is fluence and the frequency of the second event decrease over 1 order magnitude after. So the initial phase, like 100 million years, the dose become higher and this become lower later on, and that is a very important process. Okay, and now I'd like to introduce like a couple of the planetary system, like sorry, can I share the different slide now? Do you know how to share? Can you? Okay, sorry. On this one. Maybe can. Okay, yeah. Okay, the final part is actually we extended that kind of a catalog for all habitable planets. So there are 50 habitable planets. And I just want to show the one by one, like individual case. But this I illustrated, for example, that planet, like GJ1363, they have a like a super size and mass, say, and spectral type is here. And what we can calculate the annual dose of the extra surface, exoplanetary surface, and also the annual dose of the terrestrial medium. So you can calculate the dose, and also you can calculate like atmospheric escape rate. So how can you calculate the atmospheric escape rate? Is that one? We synthesize the spectrum from all host star, but mainly we use like observation data carried out by the Kevin Price and also their group. They have published like mega massive probably, and there are 23 scalar spectrum has been released, and but this is not enough for all habitable planets. So what we did is by using the temperature and by using the velocity number of each host star, that we have two hypotheses, like the shorter, longer wavelengths, like visible ray and also the infrared, will be in proportion to the temperature of the star, which means the temperature dependent. However, the shorter wavelengths, like XUV, will be depending upon how the star is activity of the star. So in this case, we use the activity of the star. It's a velocity number. So this part, we use the velocity numbers approximation, and this is a temperature approximation. And by using this, you can calculate like DJ 180, and they have very high atmospheric density here compared to the other, and also like GJ2. So we can have 50 stars, 50 planets. So each individual planet, we calculated like XUV and also the dose by the different flare. So some of the planets are very critical condition. Like here, it's a 6-7, and also the higher atmospheric escape. So this is a very difficult planet for living for our. So if we think about the future migration, sorry, I tried to share, but I couldn't find the. Sorry. So can I share from here? Sorry.ちょっと来てくれる。Sorry. これシェアできてる。あ、OK。じゃあ、わかりました。This is, I'm sorry, this I couldn't share, so I will show you but this is a Kyoto software. And this is a software that we have developed. This is the old version. Now we have a 3D version, but the old version works well because you can have a capability. So there is a star system, and you can show where the exoplanet is. Like nowadays, now you have a 5,700 planet confirmed, and most of them still in the Kepler region. However, if you and also if you just find a habitable planet, according to the Goddard and Paul, there are only 62. 62 includes the terrestrial planet too, right? So if you take a look at this, and you can have a like position of the like each individual star like this, and this software has a unique feature. So we illustrate the picture painted by student. So our student created a fancy picture of each planet. Of course, it doesn't look like this because of the tidal lock. There is a picture, the tidal lock. If the planet is tidally locked, but of course, this picture was created by a student, which means not AI. So there are some characteristics that we like, how the planet look like, or like, yeah.
So all of those are rocky planets or gas planets?
They are all rocky planet because this is the only habitable planet which has size of less than 1.9 diameter relative to the Earth. So if you include all the planets which is located in a habitable zone, become very more. It's more than 300 planets, but most of them are gas planets, like here, like this way. So half of the planet, 100 planets, is like so. This picture is just like yeah, like yeah. Some of the planet is like a very Jovian side planet, I would say. But we, for the approximation, we only choose the rocky planet less than 1.9 radius. And we made, because as I told you, we made a spectrum, actually. This was, of course, it is, we synthesize by using the massive, mega massive data, and also the approximation by using the Rossby number and also the temperature. You can calculate how much XUV for each planet and also how much UV. So by using this, you can approximate how much atmospheric escape may happen. And also, you can, for the individual planet, you can calculate like those. And for example, if you have like for the different spectrum. So in that case, for example, here, so you gave a question like if you have this is a gray and silver, and you can calculate gray and also the silver, and you can calculate the different spectrum. So this is just different spectrum. However, here you can choose the type of the atmosphere, like terrestrial atmosphere here, and carbon dioxide atmosphere, and this is a terrestrial atmosphere, and hydrogen atmosphere. The hydrogen atmosphere absorbs more radiation because hydrogen can absorb like neutron more efficiently, and the hydrogen atmosphere by the same atmospheric pressure is more efficient. And also the magnetosphere, we just use the filter. So that if you have a terrestrial magnetosphere, it's become like this way. So it's become 1/10 or less, depending upon each planet. So you can and so if you have a higher magnetosphere, you can reduce significantly. So this is software. So we can estimate for all planets you have. So for example, here, the typical functional Kepler, like a Kepler 62, is one that have been considered the habitable planet. But I think the Kepler 62 has a very good feature for the unit of the dose. It is also significantly high. So I would migrate to the Kepler 62 in terms of magnets. And also recently, Vladimir is proposing considering the neutron of the central star. The impact of the neutron also will be incorporated in the next button. Okay, so today I will finish my talk with this, but finally, before closing, I just want to show some of the picture of the sun. So this is so this is what we are trying to show as an imaginary future with the artificial gravity facility. Sorry, I want to show the music because I composed that music, but I will show the link. For example, here it is a Mars gas, and the idea was created by Mr. Horner, and also this is our imaginary vehicle. We call it a hexatron. So you can move from the one planet to the other planet by centrifugal force with the artificial gravity. This is like a train and moving to the other star system. So from the Earth and from Mars to the Neptune. And we created this just for the educational purpose, like here. So if you move to the if you arrive the Neptune. So Neptune, there is no colony yet that we don't stay in the Neptune. But if we move to the different planetary system, like in this, we make an imagination like a TRAPPIST system, and also after the TRAPPIST system, we created like movies. Oh, this is the TOI 700 was found by Vladimir, right? So you are the one that you have. So we compose the music and also the image, and in order to for the educational part. I know that NASA has already developed much more fancy animation that we also created, and we're trying to disseminate the education for the planetary system. Okay, thank you very much. Thank you.
Thank you.
Okay.
Any questions?
Yeah, anybody?
Yeah, you covered so many topics.
Yeah, sorry. No question for online or somebody?
Oh, sure.
Desmond. If anybody online needs a question, just go ahead and unmute.
So how can you, should I, if somebody wants to start,
Yeah, looks like it doesn't see any.
you go. No. Okay. Yeah, so if somebody wants to listen,
Yeah.
Can you check the chat?
okay.
Yeah, no, I can see,
There is none off.
yeah.
Okay, well, we want to thank you again for a very nice presentation. Thank you. Thank you.
Thank you. Thank you. Thank you. Yeah, and I just show the movie. We have seen the swimming. Thank you, Lord. And I appreciate it. Thank you. No question. No question.
Yeah, so what is the quick answer of that question? Are we alone? Just I'm curious. Because this last thing it came in your movie, so.
I see. Yeah. The movie is just showing the different planetary
And the
system.
question is, are we alone?
Yeah, we
What
are.
what is your thought?
And we are not alone. But hopefully that we can detect the signal from alien with that some technological innovation. I don't know how, but this is possible. But the important thing is, if you really think about moving to the other star system, you have to check whether the ionizing radiation is high or not before you are going ahead to the star systems. So better check before. Yeah. And it is very dangerous to fly by those dangerous active stuff because the radiation is very, very high. So you have to have a special people to protect. But it is very difficult to build the South Star system, which can protect from the very strong ionizing radiation because it's each may become very, very heavy. Right? So you have to fight against radiation. Yeah. So thank you. Thank you. Thank you all.
Yes, thank you.
Thank you. Thank you.
Yes. Yeah. Very good.